All right, so my name is Anthony Travaglini, and I'm an electrical engineer here at Dielectric. I've almost been here for almost 5 years now. I started out designing antennas, and about a year ago, I switched over, and now I'm working on the filter side. That was a pretty big jump, but definitely enjoy it.
Awesome.
So today's presentation is going to be discussing the importance of real-time monitoring and the next generation of monitoring systems. Firstly, I'll start off with discussing common minor issues that are encountered relating to antenna and broadcast system installations that can lead to major issues as well as collateral damage from those issues. After that, we'll discuss the importance of current practices, but with an emphasis on the shortcomings inherent to these practices. And then after that, I will discuss the approach to establishing the next generation monitoring system. And I'll close with an overview of the results obtained during our prototyping and development and testing phases. So to begin, I'd like to show you what can happen to your system when it's not being monitored live. It's a short, fun little video. Maybe you've seen it before. But it was a very bizarre situation where either a squirrel or a woodpecker decided to store its acorns inside of the dish. It took...
Go ahead.
Oh my God. So were any of those roasted, I wonder?
That's some of them had to be, right? I'm not really
Really
quite sure
steals
the
in the
power.
flavor.
Yeah. I don't know what kind of power they were using, probably not extensive, but yeah, that's about 5 years of accumulation.
Can you imagine how many trips it took for that squirrel to do that?
Yeah, it's very impressive. I'm not sure he was able to get in there to get him out, but so basically, given that it lasted 5 years before they had a complete failure, during those 5 years, they did happen to start noticing degradation issues until finally it just completely failed. And that's kind of analogous to what we kind of see in today's day and age, where things slowly break down until there's an arc, and then it just runs away from there. Slide. So the fundamental purpose of real-time monitoring is designed to monitor transmission line and the associated components. Transmission line is a vital component in a broadcast system, and the installation of the transmission line is a tedious but crucial process that must be done with tremendous attention to detail. It's very easy for someone like me to say that because I sit on the ground and use computers and I'm not 1,000 feet up in the air handling this extremely heavy but fragile equipment. Components and joints can become susceptible to failures over time. The longevity of some crucial elements are the function of antennas usage and cycling. So constant cycling will cause the contraction and expansion that will reduce the life expectancy of components and mainly the transmission line. So if it is more beneficial to keep your system running all the time. Each component in a broadcast system is handled by several people, beginning with the manufacturing and ending with the installation. So with this being said, there exists an element of human error in every sequence in the stage from being built to being installed. While quality control and inspection deters many of these potential risks from entering the field, it also contains its own element of human error, and these things do happen. So these are some minor field issues, as you can see in the next couple of slides after that will also be more minor issues as well. These are considered minor because they're recognized during commissioning, or they were found during the sweep process, and they were not subject to full power, which had they been, then they could have been a lot more catastrophic. You see the image on the left here has a warped insulator. The one in the middle, you can see can you see my mouse?
Yeah, we can see the mouse.
Okay. So up here up in this top part of the picture, you can see that the contact edge has been folded over, and that would become catastrophic if that was under full power, and if it was gone unnoticed, because you're going to get a lot of series arcing between the two joints, and then over time that would just expand and turn into multiple sections of transmission line, or even worse, more lines becoming burnt up or affected from this. Then you can see the last one during the installation here, the spring finger wasn't properly inserted, it bent out, and that right there would also become a huge concern, as that causes the impedance to not be 50 ohms anymore, and it's going to be a lot less, as well as the increased electric field at that point due to the edges being sharper and not being encapsulated inside of the inner in the line. Okay, so right here shows I just kind of mentioned that has the folded contact surface on the gas barrier. Most likely occurred during transit or installation, as it would never leave the factory this way. This discontinuity creates an area susceptible to series arcing from the outer conductor to the outer conductor. And then over prolonged concurrence, the impedance mismatch at this location increases, and then arcing becomes more frequent, and the metal will continue to deteriorate. This issue could involve, this could evolve into saying inner to outer arcing, eventually leading to component failure, and the transmitter would see this and then not let you turn itself on. And at that point, you're going to see melting of the insulator, as well as anything that, if this was in the vertical section, any of that would then just fall down due to gravity. And then figure 2 here shows a transmission line connector with a pinched Teflon insulator. The insulator was pinched between transmission line field flanges during the installation. Similarly, O-rings can become easily pinched between these flanges and are equally dangerous to the system, as they don't have the greatest contact with that in there. The pinched material introduces an undesired dielectric between the outer conductors, minimizes the contact surface between components, and creates a strong potential for series arcing. Depending on the magnitude of the contact surface separation, as well as the location of the pinched component, this may not be diagnosed during commissioning or a sweep. In figure 3 here, we have a buildup of carbon material that can be seen on a Teflon insulator on a vertical section. So whatever happened, it was above it and fell down. This carbon material could have been the result of debris or dirt deposited in the system that was not cleaned prior to the powering of the system. Excessive buildup of the carbon material, if gone untreated, can result in the melting of the Teflon insulator and potentially causing a fire inside the transmission line. These events can cause significant damage to the entire systems and are not localized to a particular area. The remediation process is both extensive and costly. Remediation process consists of breaking each joint, sweeping off debris, cleaning the Teflon with denatured alcohol, and then connecting the flanges again. This process would need to continue from the point of interest downward to ensure that all of the debris was removed. Figure 4 here, we see the split bullet on the connector. The split finger on the connector reduces the surface area of the conductivity necessary for effective signal transfer. And the distance between the outer conductor and the inner conductor is also reduced, creating an impedance mismatch. And that's going to further your heat. The heat is going to continue to increase due to that impedance mismatch. And then that'll just run away. And if it doesn't melt the Teflon, then depending on your power levels, you're going to see arcing from the outer to that point. The arrow in this photo shows the nose guard protector of the contact fingers, designed to facilitate installation and reduce the likelihood of split connectors. This was still it was intact during the time of installation, so it still didn't solve or do its main purpose to keep all those fingers inside the inner. In these instances, they seem kind of they seem important, but the things that could be caused from these would have been way more catastrophic had they not been found. So it was lucky that they found these when they did before the system saw power. So these slides will show basically the collateral damage that ensues from something that starts out small and grows to become a large event. So let's see, collateral damage. The fault detection circuits and fail-safes built in today's transmitters are relied on and tremendously trusted. In the case that a transmitter fails to shut down, a real-time full power monitoring system is an added layer of protection. And these photos are from a RFHAWKEYE site that was on the unfortunate end of a non-functional transmitter fault detection circuit and never shut down. Figure 5 here, it shows the anchor bullet connector with a melted Teflon insulator. In absence of the Teflon, the inner conductor was no longer stabilized and centered inside of the outer conductor. This allowed the inner conductor to move freely and caused a fluctuating impedance mismatch that eventually led to complete failure of the connected structure. The debris from the melted Teflon coats the inner conductor and littered the line below it. And the presence of the debris lowered the handling capability of the line. This is a pretty powerful picture showing the level of destruction that can happen when component degradation goes unnoticed. Without the supporting connector component, nothing stabilizes the inner conductors below it, causing a domino effect, and the inners just fell down right on top of each other, domino effect, and stacked themselves right inside of the outer. Actually, when they were going to take the flange apart, they weren't able to undo the bolts and pull it off. They had to use a sawzall and just cut right through the tube, and then they found that. It's an interesting find, I would think. All right, this figure 7 shows the collection of all the melted insulators that's stacked inside around the inner conductors inside the outer, and all the pile of soot that resulted from the combustion that took place inside the line. And then this final image is to show basically the trickle-down effect that happens from a serious fault. The collection of Teflon, brass, and copper debris was gathered from various Teflon pieces at different flanges along the vertical section. And this debris is so fine that it can travel through basically the tuning holes located in the Teflon insulators. In the isolated fault can incur widespread damage and extensive downtime, as it would take many weeks to comb through each section. So the overall goal of this in-depth analysis of minor issues resulting in collateral damage is to prevent this from happening again. A live monitoring system can prevent failures in transmission line through early detection of degradation and frequent arcing. It can alert the user with a high level of accuracy to the location of the fault, and preventative maintenance can be scheduled ahead of time rather than in an emergent fashion to mitigate the costs associated with the maintenance. So, and then once you get an idea of where the fault is, you can get preventative maintenance in there to schedule a cleaning or to fix if it's something minor. And you can schedule that ahead of time rather than trying to get an emergency phone call up to many people to see what can be done to get somebody on site. All right, as a discussion about the current measurement practice is important in understanding what these practices are intended to do, as well as where they fall short. Upon complete installation of an antenna in a transmission line feed system, a commissioning system characterization is performed through TDR measurements, time domain reflectivity. Once a system is given the seal of approval to broadcast at full power, the only continued monitoring system for the life of these transmission lines and components tends to be the forward and reflected power measurements that the transmitter continually monitors. Arc detectors monitor the occurrence of arcs within a system and log the appropriate data accordingly. TDR measurements are performed while the system is off air under reduced power during the system's commissioning, or when there's an issue and it needs to be located. So the power is cut, the line's opened, you attach a transition, and you use your VNA. The measurement is used to create a benchmark. When it's used for the initial, creates a benchmark or baseline for the initial system characterization, and to find anomalies that could be present during installation or anything else. Maybe it was missed at the manufacturing plant. The TDR provides valuable information by localizing faults and the presence of impedance mismatches. Excuse me. The forward and reflected power monitoring of a system is analyzed by the transmitter, or if you have another unit that does this. These measurements are typically quantified as VSWR and be conveniently displayed on the transmitter's digital output screen. This information can be influenced. It can influence the decision to shut down a system due to the uncharacteristic performance. And then arc detectors are able to identify arcing occurrences within a system. They also have the ability to interlock with the transmitter to reduce or discontinue transmitter output power. However, each of these measurement practices may be, however important these may be, they each fall short to what is necessary in today's industry. The forward and reflected power measurements is an aggregate response to the entire system's performance. These results are difficult to interpret. It can inherently not discern benign changes from an antenna's performance to potentially dangerous changes located inside the transmission line. A broadcast system performance will change significantly with the temperature and other environmental factors at the antenna level. A 1.02 to 1 to a 1.05 to 1 VSWR change is rather typical given various weather events, seasonal changes, storms, ice accumulations on antenna radomes. But if you were to have a 102 change of VSWR at a connector, that's a pretty serious indicator that something isn't working the way it should be. Arc detectors are able to identify an arc occurrence, but cannot localize the occurrence. With some systems consisting of 2,400 feet of transmission line, an arc detector provides an important bit of information, but leaves the diagnostic and repair like searching for an electron in a vacuum. TDR responses, they measure basically the time domain of the system under limited power. Under this limited power, anomalies can potentially go undetected, and the results can only be used as an initial characterization and cannot continue to compare the system's performance to its baseline. Performing this measurement requires a system shutdown and a qualified field engineer to perform it on site. So the next generation of real-time monitoring systems is to implement a system that can be retrofitted into existing sites. The system has the ability to detect and localize arcs and discontinuities due to changes in transmission line integrity. It will characterize the system over time, and it will also allow for discrete alarms to be established based on component characteristics. The system will operate full-time under full power conditions through the use of off-band injection. The system consists of a coupling unit, which is right here, the transmission line, which then is connected to a processing unit. And that itself, that processing unit is connected to the central monitoring unit, which is where you interact with the unit itself. The coupling unit is manufactured to the same size transmission line, and it is installed post-filter and post any waveguide. The signal cannot propagate through waveguide. And it's usually installed before the gas barrier because it's not pressurized. The strategic placement of the coupling unit after the coax switch allows for the continuous monitoring of the system, whether or not it is in operation. So this will continue to monitor your transmission line, whether there's full power from the transmitter or no power at all. The results of this can be very telling, identifying temperature dependent mismatches by comparing measurements while the system is off and after while it's cooled down, or vice versa. Traditional TDR measurements cannot achieve this because the system will have already cooled down by the time the test setup is complete. The coupling unit is designed with 2 injection ports, allowing a wideband VHF signal to be injected into the system. The design of the injection ports is to create a strong coupling factor of the VHF signal onto the line. The injection ports are separated by half wavelength at the antenna's system's design channel to make sure that none of the UHF power actually sees its way into the processing unit. The processing unit provides real-time data, while the central monitoring unit boasts an IP interface for remote monitoring. The nature of this IP connected system will alleviate the monitoring duties necessary for individual broadcasters. Today, transmitter fail-safe circuitry is highly trusted and the only method used for system protection. As shown previously, collateral damage does occur because these fail-safe do not operate at a 100% success rate. With the current monitoring products on the market, many questions linger. When an arc is detected in a system, but the transmitter does not shut down, what's the plan of action? Do we continue to broadcast on the main antenna and disregard the event? Do we switch to a potentially inferior system on the aux antenna and reduce our coverage to schedule maintenance? If the arc does incur a shutdown of the transmitter, what's the plan of action then? Do we turn the transmitter back on and hope that it's an isolated event? All these questions become ambiguous with the presence of a real-time monitoring system. The system can detect changes in return loss of less than -45 dBs and with a localization accuracy of plus or minus 18 inches. And the system does meet or exceed the FCC out-of-band emission standard of less than 110 dB on carrier. And the system can also detain sustained arcs greater than 100 microseconds. And so in conclusion, I've shown that many minor issues are encountered during the installation process of a broadcast system. And some of these can, and unfortunately, aren't necessarily seen on low power commissioning sweeps. However, these system anomalies go undetected and they result in failure events. And whether or not the system has a potential way to shut down before it becomes catastrophic is the biggest concern. In current practices today, it's really important to have these tools for monitoring these broadcast systems to prevent complete shutdowns and catastrophic failures, so that you're out months trying to rebuild the system. So with that, I thank you for listening to our presentation. And if you have any questions now, you can ask those. If not, if there's time, I can show you a little demonstration of the graphical user interface for one of these systems.
I'd say go right ahead with your demo.
All right. So there's different levels of credentials that can access these units. There's a user level, which you have very limited functionality. It's basically read only. And I can show you after an admin level, all these menus open up to allow for setting changes. Okay, so you come in and you get a dashboard. Usually this site doesn't have anything populated on it, but you can put up your VSWR chart and your open alarms, and those will show you kind of what you want to see right away. And then any open alarms would be present here. And this site hasn't had anything that happened lately. You go to the closed alarms, and then it'll show you all sorts of things here. So for instance, this week we got a degradation warning here. Tells you the date. It tells you how many times it happened. Its first occurrence, the last occurrence. And it gives you a location, and it'll give you the threshold number as to why it alarmed and what its current value was. There's all sorts of warnings. You can choose which ones you want to alert you, and you can set all those thresholds manually. So if you know what your system performance should be during the summer, and then you notice during the winter it elevates a little bit, it can be mindful of that. But the most telling sign of, or the most, I guess, for me, the biggest visual from the system is the TDR plot. And so you can zoom in and out. And then okay, let me close some of these. So when you get your baseline when you first install and commission the system. And that baseline is what is going to determine what your warning threshold and then your alarm threshold is going to be. Currently, we have an algorithm that determines what those thresholds are. They can be set to anything you'd like. So if you know the performance is going to get worse over the winter months, then you can go in and change that. But so when you hover over a marker here, it gives you the location at 121.8 feet. The blue gives you the current measurement. The yellow is the warning threshold. The red is the alarm threshold. And then your blue is your baseline, which it's comparing it all to. So if your current measurement would happen to cross the yellow threshold, you would then get the degradation warning like we saw here. And if it crosses the alarm threshold, then you get the alarm. And then from there, you can determine which actions you'd want to take. We are currently in the process of developing an interlock connect so that you can have that set to shut the transmitter down itself, or you can just rely on human intervention. Sorry, I'm losing my voice. And then you can go to the this arc histogram. It'll kind of give you basically in the last minute, the last hour, last 24 hours, 7 days, month, and then all time. And it'll give you the number of occurrences on the Z-axis. And then it'll give you a location marker across the X-axis, if you want to call it. So if you were to have an arc, it would populate up, it'll show you, and then as time progresses, it'll move its way to the back. And it'll show you if it's a warning, it'll be yellow. If it's an alarm, it'll be red. And then we can also go here to, there's a power monitoring option, and it gives you a little scale here. It has the potential to give you the temperature and the humidity if these sensors are attached to your system. It could be beneficial if you know what it's doing. And then so here you get your forward power, your reflected power, and then that calculates your VSWR. And even that's current. And then you can take this and it plots it over time. So you can go back and see when there've been events that have happened. And in this particular site, KATV in Little Rock, Arkansas, they had a pretty bad event. We've determined it to be a lightning strike. It basically shut down their entire system. They were, for a few weeks, they weren't able to go past, I believe it was 20 kilowatts forward, when their normal forward is about 50. The transmitter would just trip off. And then so it tells you use your forward power. There was a dip. And then it showed when it came back up. And then the corresponding VSWR is the red line. And here are the set thresholds for that. So you can have a VSWR alarm, you can have a degradation alarm, you can have arc alarms. There's many alarms on top of all of the alarms that monitor the unit itself. And similarly, it shows you get the environment and the humidity, or temperature and humidity values at the site. This is internal to the system, since the site doesn't have any sensors. So it's what's inside the CMU box, which is being read here. But you can put a temperature or humidity sensor anywhere you want, and as many of them as you want as well. And then so if I log out, I go back in. Now this is an admin credential. And so here you see under the configuration pane, you got basically this, wherever you want to set up your warning values, your limits, any information about the system. All your network stuff here, you can have it send text messages, you can have it send emails, you could have SNMP. I don't know if you guys utilize any of that for remote monitoring, remote access on your sites. We also have a new tool. It's basically a centralized server that all these units are connected to, and I'll show you that after I'm done this part. Here is all of the warnings and alarms, and you can tell it what to do, whether you want it to send an email or send your remote access the alarm for it to do something at that point. Most of these are related to the unit, so that if say the PU stopped communicating to the central monitoring unit, then it gives you that error. Right here, it's the PU disconnected. And then here you can set up users that you want to put into the system, and you can choose their role as to what they can do. Just a log of everything and diagnostics for the system. And then coming down here is just where you would set up any sensors you have, directional coupler sensors, environmental sensors, and whatnot. But then so going back to the analytics, this is the site that you would log into it, and any sites that you have, if you have more than one site, you can attach all those and you can monitor them. We have currently 15 in the field right now, and it's a quick thing. If there was a problem, like over here, we have a yellow, it's a degraded issue. And that was due to, I believe, one of their RF detectors. It's a power glitch. And then so that needs to get reset, and then it'll go green. But then so basically after you've clicked onto your site and you want to see it, if you want to go to the GUI, you would, under here, you would just click, and then it brings you to your login page. And you could do that from anywhere in the world. But yeah, that's kind of the breakdown of our system. You guys, any questions, comments? Did I put everybody to sleep?
I see one in the chat here. We have a system here with 2 transmission lines for upper and lower antenna sections. Can one central monitoring unit do both?
Yes. I believe you can have up to 4 PUs attached to one CMU. So you can monitor up to 4 units with one central monitoring unit, or 4 lines with one central monitoring unit.
And before I forget, thank you for the sponsorship, by the way.
Yeah, no problem. Thank you. We appreciate the opportunity to present and interact with you guys. So I will say too, we have the we're ongoing with the interlock connection. I don't know if that's a big selling point for a lot of people. It's kind of mixed that I've seen on my end. Some people like it, really want it. Other people, they could care less. But we are also in the process of making, so basically the unit we have now is kind of for high power broadcast systems in order to meet the FCC's out emission standards of 110 dB on carrier. So as you get down to lower powers, you're not going to get that margin. So we're in the process of creating a lower power unit as well, which would then still meet the FCC's requirements and do what we want it to do on our end and actively monitor and characterize your system. But there's a
So I do have a question. We're a part of a group of, there's a 9-station combiner that's in auxiliary mode on the top of the IDS building in downtown Minneapolis. And because it is an auxiliary, obviously it's not on all the time. When we put the system in 20 whatever some odd years ago, we purchased the system with a monitor protection system, but could never really get it to work because of its part-time status. So do you have thoughts or comments on that particular mode of our operation?
yeah, so but I have a question first. So when the system wasn't powered up, the monitoring service wasn't actively or correctly working?
Correct. And that is true of, we never really could get the system to work correctly because when everybody was off and supposed to be off, the system was saying error, error, error.
Right.
But yet, we were supposed to be off. So there was no way that we could figure out to trick the system to say, yeah, we're supposed to be off, not,
Right.
So it's kind of a tricky scenario.
Right. So so this unit will monitor your forward and reflected power on channel, as well as give you the TDR. So when there's no forward power, your directional coupler reading, it won't be accurate. It probably gives you an alarm saying that you're probably like a 4-to-1 VSWR given, or probably even negative given you probably have more coming back down the line than you have going up the line. We've seen that on our system where you turn the forward power off and it kind of sends you an alert saying, hey, look, the VSWR skyrocketed. I mean, we've mitigated that, but at the same time, the TDR function, that's constantly running. Even if your system, even if the transmitters are on or off, you're going to see a real-time TDR of the system, regardless of what's happening. So that would then alert you to, if it crosses thresholds, to say, hey, look, there's a problem, don't turn it on, or everything's fine. Continue with moving whatever stations you need to this aux system.
Well, that would be helpful, or that would be an improvement over what we have, which is currently nothing.
Right.
Okay.
I'm going to add my contact information to the chat box. If anybody has questions or something pops later, you can message me or call me.
Absolutely.
Yeah, no, it's definitely there's a huge benefit of being able to look at a real-time TDR without having to go through the whole process of scheduling a shutdown and getting a VNA and everything on site. And there's a huge benefit. The only thing I didn't really mention, and it's not a drawback per se, but given, like, I think this WGME website. So right here, you see that there's a big spike. It was. It's right here. You got a nice big, a pretty large bump that you would probably consider concerning on channel, like on the system's frequency. But given that this system uses VHF component, a VHF injected signal, sometimes your components are frequency dependent. And in this case right here, we're looking at a, I believe it's a 675 to a 650 transformer. And it doesn't look great at VHF signals. So that's why it looks more elevated than it should. But if you just characterize it during the sweep and the commissioning, then it's, you know, that's what it is. And if it were to change from there, that's where you have your issue. And the same with the antenna. The antenna's frequency at VHF looks horrible as well. And that's why you then see this huge fluctuation from your VSWR. So it's not like you can really compare apples to apples, given that if you have a UHF system, it's kind of sweeping the signal with a VHF signal. And then we also too have, so this, the one I showed you today, or the way I talked about it, was using UHF, using like UHF antennas, but we also have it where you can monitor FM or VHF antennas as well. And at that point, it sends a UHF signal up the line so that it remains out of the FCC's out of mission standards. And you can hook up, if you have a panel antenna or you got a multi-channel system, we can handle that as well. But yeah, and then you can see up in the top, the top up here kind of gives you your antenna status, which is information from your directional coupler, forward and reverse power. And then that in junction with this TDR is kind of how you can kind of, if you see an increase in VSWR, but you don't find any anomalies in the transmission line, you can kind of point your sights towards the antenna. Vice versa, you can, if you see an increase in VSWR and then you're also getting degradation alarms or warnings, then then it gives you a location. Makes it a lot easier to troubleshoot and takes away the variability of looking for it. But that's all I have.
Any other questions?
I'm sure some will maybe pop up later, so don't hesitate to call or email me or anything.
Oh, hearing no further business. Thank you very much, sir, for your time.
Well, thank you very much.
Yeah, appreciate it. Thank you. Let me see if I can send this back to you.
And Taylor, I don't think that we have any additional business unless you do.
Nope, not on my end. Anthony, I'll get the, for lack of a better word, invoice over to you and Kim.
Yes. Yep.
All right. Hearing nothing further. Have a good
Right.
day, everybody. Thanks for coming by.
Thanks, everyone.
Thank you.